Let's begin this video by taking a few notes. If you do not have this friction and force formula, friction and force page, and the friction experiment time page printed out, I'd like you to press pause and get them printed out. You will need the friction and force student notes and the friction experiment time pages printed out. Okay, let's get started with this. Friction and force student notes. The first thing at the top of the page there, you see the word friction. We will be experimenting with friction this week, so it would be good for us to know exactly what friction is. Friction is forces acting between two surfaces, holding them in place. Go ahead and fill out the definition there of forces. Forces acting between two surfaces, holding them in place. If you notice the little picture there at the top, something is really holding this box in place, okay? And he's trying to pull it, so there are forces that are causing him to not be able to pull that box. Just normal forces that we have on Earth. Take a moment and get that definition filled in. Friction, forces acting between two surfaces, holding them in place. Okay. Let's go on. If at any point you need to pause the video to finish copying down, go ahead and do that. Let's move on to types of friction. There are two types of friction: static friction and kinetic friction. For our purposes, we will be looking more at the static friction. Go ahead and fill out the two kinds of friction. Two types of friction: static and kinetic. Okay, the next thing we see there on our notes paper is law of inertia. Law of inertia is one of Isaac Newton's actually his first law. And when we see what law of inertia is, we look there and we see a guy standing in a red box. And this helps us to remember that the first part of the law of inertia is objects at rest want to stay at rest. The man in this box is not moving. He is standing at rest. So the first part of the law of inertia is object at rest wants to stay at rest. Go ahead and fill out the first part of law of inertia. Okay, the second part of the law of inertia, we see a man in the green box there who is moving. So this kind of should trigger our brain to help us remember that the second part of the law of inertia is objects in motion want to stay in motion. Very similar to the first part, objects at rest want to stay at rest. The second part is objects in motion want to stay in motion. Go ahead and fill out the second part of law of inertia. Object in motion wants to stay in motion. Okay. As you're finishing that up, I want to explain that the reason why we discuss the law of inertia when we're talking about friction is because when things want to stay in motion, what causes them to stop staying in motion are frictional forces. So if you're sliding something across ice, it will continue to stay in motion. But if you slide something across the carpet, it doesn't stay in motion the same way as it does across ice. So you can see that there would be more friction with carpet than there would be with ice. So when we are talking about the idea of friction and force, it kind of goes hand in hand with Newton's first law, the law of inertia. Objects at rest want to stay at rest. Object in motion wants to stay in motion. Later in the week, you'll be watching a video that reviews that idea of the law of inertia. Let's move on to coefficient of friction. Coefficient of friction is actually a math formula. It is force applied divided by normal reaction. You may be wondering what force applied and normal reaction are. These are actually already things we've talked about. Force applied is the same as force in. That is why they're both F. So force in, F, or also called force applied in this case, divided by R, normal reaction. And if you remember, R is the weight or resistance of the object. So it is force in divided by the weight, or the force out. For these purposes, we are also going to call, aka also known as scientific weight, the normal reaction, the weight or resistance, we're going to begin to call scientific weight. So your R is going to be what we will call scientific weight. The normal reaction is the scientific weight. Scientific weight is a little bit different than just weight. We'll see that in just a minute on down the page. Go ahead and fill out the coefficient of friction things that I have written here. Force in, F, force applied, divided by R, normal reaction, weight or resistance, also known as scientific weight. That's a lot of words. So if you notice here it says or ratio. Let's simplify this just a little bit. Force applied, F, divided by normal reaction, R. F over R. A little bit easier to remember, and if you compare this to the mechanical advantage formula, it's actually just the flop of it. Mechanical advantage is R over F. The coefficient of friction is F divided by R. Now remember, if you're getting behind and you need to fill out any of the things that we've done so far in this paper, press pause and get everything filled out. Then you can press play to continue. If we continue on, we see symbol used. There is a special symbol used for the coefficient of friction. Instead of writing out the words coefficient of friction every time, they use the symbol mu. It looks kind of like a U with a sort of stick on the front. It is mu. M-U is how you pronounce it, mu, and it is a Greek letter. Go ahead and write the Greek letter mu and the words mu Greek letter. This is what we will be calling coefficient of friction in our formulas and things. Much easier to write than writing out the whole words coefficient of friction. Another term that we need to be aware of when dealing with force is acceleration due to gravity. Now, we all know that there is gravity. Gravity is what holds us to the earth. So unless you're floating in your chair right now, then you are being pulled to the earth with gravity. So gravity has some effect on friction because gravity is pulling things to the earth. So we need to know the acceleration due to gravity in order to do a few things. And in order to do some calculations with friction. Acceleration due to gravity is how fast gravity pulls something to the earth when it is dropped. It also has to do with that pull to the earth. So even if something's not falling, the earth still has a pull on it. The number for acceleration due to gravity is 9.8 meters per second squared. That's really close to 10. So for our purposes, we're going to round it and use 10. That makes a lot of calculations way easier. So acceleration due to gravity, while it is 9.8 meters per second squared, we're going to use 10 meters per second squared. Now, if you noticed just a second ago, my R dropped in front of scientific weight. R being normal reaction, being the weight or resistance, we are going to now use the scientific weight. Scientific weight is mass times acceleration due to gravity. Your mass should be in kilograms, and we're going to multiply that by 10. Anytime we multiply a mass by 10, it's rather simple. Since there's 1 0 in 10 and we're multiplying the mass times 10, we'll just move the decimal place one spot. But scientific weight is mass times acceleration due to gravity. When you weigh yourself on a scale, that is not your weight. That is actually your mass. So when we are talking about scientific weight, we need to remember that we are multiplying that mass of an object by 10. In other words, we need to move that decimal place one time. So don't get confused. When we are speaking mathematically, weight is actually mass. Scientific weight is when you take that mass and you multiply it by 10, the acceleration due to gravity. So for our purposes today, we will be looking at static friction formula, and I have two versions of it here. We will mainly be using this second version. Okay, we have F equals mu times R, and we also have mu equals F divided by R. The second one here is the one we will be using. Okay, so for our experiment, that is the formula we will be using. Some things I want to point out on our worksheet here. One, here in this formula, you're solving for force in if you're trying to figure out the force you need to put in. I also want to point out that the scientific weight is the same as R. Remember all that really wordy thing up there in coefficient of friction, R, normal reaction, also known as scientific weight, what we've called weight or resistance so far. Well, that's the scientific weight. Okay, so for that R number, we now are going to be taking the mass in kilograms and multiplying it by 10 for our experiments. Like I said, not real hard. All we have to remember is when we are trying to figure out the R, if it gives us kilograms, we just need to move the decimal one place to get our scientific weight. Here, we can see in this first formula that R is the scientific weight. R is also in this formula. So scientific weight is one of the things that we would need for both of these formulas. As I said, we will be using the second formula for our experiments this week. We will not be using the bottom of this student notes page. I've actually copied it over on to your experiments page. So you can put an X through these. We won't be using them on this page. You'll see on your experiment page that I have them in the middle. Right there they are in the middle, and I've even given you a few things to help you fill them out. Before you go to the experiment video, okay, I want you to look at the top here. The question is, which material will show to have the least amount of friction? The carpet, the pipes, or the marbles? We will be doing a friction experiment on carpet, on rolling pipes, and on marbles. Before we begin the experiment video, I would like you to fill out your hypothesis. Okay, which one of them do you think it will be? This is your hypothesis, or your educated guess on which thing you think will have the least amount of friction. Will the carpet have the least amount of friction? Write carpet in beside hypothesis and tell me why. Will the pipes have the least amount of friction? Write pipes in and tell me why. Will the marbles have the least amount of friction? Write marbles in and tell me why. You choose one of those three to put in your hypothesis and your reason why. Then I would like you to move on to the experiment video. So you will need to fill out the top of this page before you do the experiment, where we find out truly which one has the least amount of friction. Once you have that finished, then you can move on to the experiment video.